So, starting the chapter of potential and capacitance, these topics potential energy, capacitance, and dissolve. First thing is potential energy. So, we know that the whenever there is a conservative force, there is a conservative force, then the work done by conservative force is equal to the negative of the potential energy change in that conservative force. So if there is a conservative force, let's say electric field, electrostatic field is there, then with respect to the electrostatic field, the work done by electrostatic field, this is the work done by electrostatic field, then negative of this is equal to the change in potential energy in the electrostatic field, and potential at u at infinity is taken as 0. Means if there is charge here q, then the potential there is a charge q here and there is a charge q2 here, then the potential energy of this charge would be equal would be 0 if the distance between them is infinity. Means with respect to this q charge, this charge will have some potential energy, let's say some constant value q times q2, that is the potential energy of this q2 charge with respect to this q charge. So due to these two charges, this q2 charge will have energy u, and when this q2 charge is at infinite distance from this q1, then this u will become 0. Means this is somehow related to kq2, and the potential energy at infinite distance, we are taking it as at infinite distance, potential energy at infinite distance, we are taking it equal to be 0. So, this is the reference for this is the reference potential energy, and now if I integrate let's say there is a charge, the work done by an electric field would be equal to electric field and to the charge q, that is the force, dot dx integrated from r r initial to r final, that is equal to the negative of delta u, that is the change in potential energy. Now if the particle is initially at infinite position and I am taking it to a r distance from this q charge, I am taking it to a r distance from this q charge, then this integration will become, since I am moving it towards this charge and electric field is pointing in this direction, both are negative, so dot product will be negative eq. The charge which I am moving is q, test charge is q, so eq dx integration from infinity to r would be equal to minus delta u, which is equal to minus of u at this r distance, which is minus of u at r minus potential energy at infinity, which is 0. So this equation will give eq, where formula of electric field is simply kqq upon x square integrated from infinity to r. Sorry, there is dot product here, there are two signs here, minus minus will get cancelled, we get ur is equal to this, which becomes kqq over r. When we solve it, it becomes u. The potential energy of the charge q at a r distance from the q is this, and it can be said in another way like If there is a charge q here, then due to the charge q, the q charge will have potential energy this when it is at r distance. So this two will have this potential energy. We can say this has potential energy due to this charge field, or we can say this charge has potential energy due to this charge. So we can say in any way both are equal. Now moving ahead, this becomes the formula of both are point charges. So for 2 point charge at r distance separation, potential energy is equal to k q1 q2 over r. Here k is equal to 9 into 10 to the power 9. But if medium, this is when vacuum is used. This is when vacuum is used. But if medium is given, then k will be replaced by dielectric constant times this k value. So we will replace this by this. So this was all that thing. Now there is another thing which is called potential. Potential means potential energy per unit charge. Potential is divided by U, that is equal to potential energy per unit charge. It is, since potential is also dependent on reference point, potential is also dependent on reference point. So we assume that V of, let's say there is a charge q here and there is a charge q here. They have a distance r, then the energy will be k q over r. That is the energy, and when I divide by q, we get p is equal to kq over r. So the potential at point p, which is at r distance from this q, the potential at r distance from point p due to the q is v is equal to kq by r due to the charge q. And here we have to note that one more thing is that v at infinity is also equal to 0, just like potential energy. So this is the formula of potential. And potential difference, there is one more equation for related with potential. So when there is a potential, let's say there is one point here, let's say A, and there is a point B here, B. These are 2 points. This point is potential VB, this point is potential VA. And let's say these are two very, A and B are very close. Very close. So we know that the du is equal to df dot dx minus, this is the equation for this. So if I divide it by charge, I will get d dot dx is equal to dv, this equation. From this we will get this equation. Now I can say that dv by dx is equal to du, or I can say that dv is equal to minus e dot dx. These two equations I can also consider here. So that's it. These are the two equations I will consider here. Important, these two equations. And in this case, let's say this is final potential VB minus VA. Let's say this distance between them is dx. Then VB minus VA is equal to dx times the electric field from times minus of electric field between them from the direction of electric field will be taken um, according to this. The electric field present between them is E, and taking its dx minus vv minus v. This is a positive value. V. This is a positive value. This is negative. And since I have, if I am assuming that vb is higher, if vb is higher than va, then this is positive. So this e value will become negative. So find that we find that if there is a potential v, this if this p point has higher potential, if vb is greater than va, then the electric field will point from b to a, means in opposite direction. If this has higher potential than this, then the electric field will point in this direction, opposite direction, from higher potential to lower potential. Electric field points from higher to lower potential. This is one more thing, that electric field will be pointing from higher to lower potential because let's say the final potential is higher, then dv will be positive and minus dx into e. Since these two are value positive, dv by dx is, if it is positive, then this value become negative, and this will be negative, means in opposite direction. Now we find that potential is equal to k q over r. So if there is any body, having charge q, then if there is a point body, this is for one more condition here, is that q1 q2 are point charges. q1 q2 must be point charges, or maybe the q1 is a sphere, solid or hollow, uniformly charged. This is q1, this is q2, or they can be solid or hollow spheres of uniform charge, and their distance between, and they are not coinciding. Means if they are not coinciding, then if this b point and this a point both lie outside their, is b lies outside this sphere and a lies outside this sphere, then in such cases, means this whole body lies outside this sphere and this whole means both are outside, they are not coinciding, then in such case I can consider this whole body to be concentrated at this point and this body to be concentrated at this point. So I can say that this whole charge is at this point, this q1 is at this point, and this q2 is at this p point. So I can apply the potential energy formula by assuming these two charges at these 2 points. Now that's it. This will work for sphere and hollow, hollow sphere, solid and hollow sphere, uniformly charged. Now moving ahead, doing some more calculations, some equations of potentials. I will directly write the equation of potential. Let's say there is a sphere, here, this is hollow sphere, this is a hollow sphere of sigma charge density. Let's say it is carrying the charge q, it has a radius r, then the potential at any point outside this, if the point p is outside p, potential at p, if p is outside, if p point is outside, then vp will be equal to simply this distance from center to this point, P is, let's say, r distance, then the value of potential will be simply k q by r. And if P is inside, then since it is a hollow sphere, we know that the potential at this point would be kq by r at this point, just outside this sphere. And since the electric field E is equal to 0 inside this sphere, hollow sphere, the ADX value will be 0, which is equal to dV. So since the dV is equal to 0, the potential everywhere in this system will be 0 because there is no change of potential. So Vp is equal to Vp at any point here would be equal to Vp below potential at this surface of this point, which is kq by r. Now this was for hollow sphere. Now if there is a solid sphere, for solid sphere of rho density, let's say there is a solid sphere with rho density of charge, let's say charge has it has total charge q and it has radius r. There is a point P, can be inside or outside. If P is outside, then I can simply treat this whole sphere as located at the center point, and the formula of potential at P will be simply kq by the distance r. I can assume that whole body is concentrated at this point. But if P is inside, if P is inside, then Vp would be equal to, if P is inside, then this distance is r, then the formula will become k q over 2r cube 3r square minus r square, where r is the radius of the sphere. Okay, so this is the potential at the point P. So this is one important thing, and this is very simple fact. This can be noted because E is equal to 0 inside. This is because E is equal to 0 inside in the hollow sphere. Now this is it. Now the potential due to, now we have to find the potential due to a dipole. Let's say we can simply use this E dot dx formula for calculating this dV potential at any location. Let's say there is a large infinite plane and we have, can be anything. Let's say we can calculate the potential for any case. For example, let's say there is a line of lambda charge density, we can find the potential at any point. That's simple, easy. Now the question is for potential due to a dipole. If there is a dipole, let's say there is a dipole, this is dipole, this is a minus q charge, this is plus q charge, this is center of, and let's say there is a random point in the space P, any point in the space P, then the position vector forms this pole to this P point is r vector, and this is the dipole moment vector, and the angle between them is theta, means between P vector and this r vector the angle is theta. This is theta, and in that case the potential at Vp is approximately, when this dipole, for very small dipole, this is an important condition, that is dipole is very small as compared to the, means if A is very small than r, that's it. I have to write this. If A is very small than r, then we can write Vp is equal to Kp dot r cap divided by r square. This will become the formula of potential at the point P. And for accurate formula, let's say if a is not given lesser or greater than r, if a is not very small than r, if dipole of finite size, then the formula of potential at any random point in space becomes very complicated. But for the potential at any point at the axis, for potential Vp at p on axis can be accurately given by the formula Vp is equal to k p dot r divided by r square minus a square. So if there is any point along the axis of this dipole, then we can accurately give the formula of this Vp by this equation. When the a value is very small, this becomes 0 and this formula becomes this one. So that's it. When the point is here, it is close to the positive charge, it will have positive potential. When it is here, when the point taken is here, then it will be close to the negative charge, so the potential will become negative. And potential energy, these are scalar value, they will have only positive and negative signs only, and they depend on the distance, not position vector. So that's it. Moving ahead now. The next topic would be, I guess, we have completed potential. Now, one more thing about potentials is that, let's say there is any any surface of sigma charge density, and it has some radius. Let's say there is a sphere of sigma charge density, it has radius r. Well, okay, listen. Whenever there is a potential difference unequal to 0, means there is a potential difference, then there would be electric field unequal to 0 between two. Means if a and b are the points such that va minus vb is unequal to 0, that implies e between a and b unequal 0. So there would be electric field between a and b, and there will be some flow of charge due to the electric field. So as long as there is potential difference, there will be flow of charge. So in case of electrostatics, let's say there is a body here, it has charge q and radius, this is r1, this is charge, let's say q2, this is q1, and it has radius r2. Then the potential at its surface, this is hollow sphere, this is also hollow sphere. Potential here is equal to k q1 by r1, here is k q2 by r2. So if I want to make sure, if I join a wire, if I connect them with a wire, and after electrostatic condition is reached, after current between them, after the motion of the charge becomes 0, there is no motion of charge here, the condition becomes static, then the potential everywhere on this body will be 0. Sorry, potential everywhere will be constant, means same, there will be no potential difference and no motion of the charge. So to make the potential constant, we have to make this v1 and v2 equal, so that there is no potential difference between these two. So there is, so if we make v1 minus v2 is equal to 0, this will, electric field between them is equal to 0, so there will be no flow of charge. So in static condition, these 2 points will have equal potentials. But if the system is just released and there is some potential difference, then there would be some electric field and this will cause some flow of charge. And one more thing about potential is that potential, as we have seen from the shape here, that occultative limit will drive leader. If let's say there is a conductor, let's talk about conductor. If there is a closed conductor, let's say this is hollow, it has some cavity inside, and this is conductor. If I put some charge here, let's say q, then it will get spread everywhere. Maybe not uniform, but it will get spread everywhere. Here sigma will be sigma 1, here charge density will be sigma 2. It will be spread everywhere, and the charge will only be lying at the surface. Charge will only lie at the surface of this conductor body, outer surface. The charge will only lie at this outer surface of the body, because if the charge lies, if any charge q lies in this region, and in such case there would be some electric field due to this charge. No, if there is some net charge, then there would be some net flux coming out of a cavity we draw here. Okay, let's just draw it. This is a conductor, this is a cavity. If there is electric field in any region here, let's say there is an electric field in this region here, then since there are charged particles in this medium, electrons in this medium, and electrostatic case, we are only studying electrostatics. Since there is no motion of charge, if there is electric field here, then and there is electron here, there will be force on the electron to move it, and there will be some current produced. So in electrostatic case, current is not produced, so electric field must be equal to 0 inside this conductor. In conductor, electrons are free to move. In case of insulator, the electrons, even if there is an electric field provided here, the electrons will not move. What will happen is that the atom will produce an opposite field in a direction by using its dielectric property. Using the dielectric property, it will oppose the electric field, and the electric field at this location will become 0, and the charge will not move at all. The electric field at the electron will become 0, means the medium will make some electric field due to the medium, and the electric field we have provided, both will add and give net 0 electric field at this charge position in case of insulator. In this case, the electrons are free to move, so it can easily move the particles. Here electrons are not able to move, it will not have any limitations. It means even if you apply very large potential electric field, the electrons will just get separated more from the nucleus. Let's say this is electron here, and I am providing an electric field in this way. It will make this path of the electron to become like this. It will shift here like this, and this will become a negative. This negative region will become here, and this side will become positive. This will become polar. This side will become positive, and this side will become negative, because electron is more present in this region, because electric field is pulling it, and this positive charge and negative charge will create a field in this direction, which will cancel out the initial field provided. So the original field provided, which was E, and this was the electric field due to this atom these two cancel out each other in case of insulator, because this can be very high in case of insulators, but in case of conductors this electric field has very small value. This is very small in case of conductor, so it cannot cancel out the value of electric field much, and the electron starts moving. It just moves out of the orbit and starts moving in case of conductor. So we can simply say that in case of conductor, if electric field is provided, the electron will simply start moving. Now the electric field inside this conductor will be zero in electrostatic condition, and let's say there is some positive, some charge q here, some charge q here. In this region there is some charge q here. If I draw a Gaussian surface here, there will be some flux coming out of it, so there must be some electric field in this region also. If there is some electric field in this region, this will violate this condition. So it means to have electric field zero everywhere in this region means E dot dA summation is equal to the flux, which is equal to the q by epsilon. So since electric field is zero everywhere, this integration should be zero, which means this q will be equal to 0. So the charge inside this conductor should be equal to 0. But let's talk about the means charge inside this conductor will be equal to 0. But what about the cavity? Can there be charge in the cavity? We will check it also. If there is a conductor and there is a cavity here, if there is a charge q here, then it will provide some. Let's say this is Gaussian surface. Just below the surface we have taken a Gaussian surface of this cavity, and there will be flux going outward if there is a q charge inside, and the flux would be equal to q by E, and that is simply equal to summation of E dot dA. So since there is a charge inside, then there must be some electric field present at these places. So at these locations there must be some electric field, and there can be electric field because we know that at the surface of the conductors electric field inside these regions is must zero, but at this surface and at this surface electric field is perpendicular to surface, means at the outer surfaces like this, which the surfaces of the conductor which are exposed to outer medium, let's say this surface or this surface, these surfaces can have perpendicular electric field like this. So this means like this or like this. Now one more thing is that the electric field at this point cannot be inside. If the electric field is inside, this will make the charge move inside. So the electric field is perpendicular. That is the first point. Second point is that electric field is outward surface. So, so electric field is outward to the surface and perpendicular to the surface. So the electric field at every point here will be outward, because no, it can be inward also, because why? Well, this is not right, because we have two types of charge. So this is only right that the electric field is perpendicular. It can be in this direction or in this direction. Maybe right. So the electric field is perpendicular to the surface, can be in this direction or in this direction. So that's it. Here we can have electric field, and this will not create any problem, because if there is a parallel component of the electric field, this will cause the charge to move. But if there is a perpendicular component, let's say it is pushing the charge outward, this will not create any current. but a parallel component of the field can cause the charge to move along this path. So this can cause current. While in this case of field perpendicular to the surface, the charge is bound by the surface. It cannot go out of surface. Charge cannot go out of surface or leave a leave a leave a vacancy of charge. Leave a vacancy of charge means what I mean is here that let's say there is a cavity here and there is some charge q here. Let's say electron is here. So if electric field is perpendicular, the electrons will have force perpendicular to the surface. So it will either move in this direction or it will move in this direction if the field is perpendicular. Since electron cannot go out of the conductor, this will stop it from moving. So it will cause the current to be zero. And if the force is in this direction, since if the electron moves in this direction, this will create a vacant space here, which will gain a positive charge due to the lack of electron, which will create a field in this direction again. So this will again cause the electron to not move. So again the charge will not move. So overall we can say that the charge will not move when the electric field is perpendicular to the surface of conductor. And this is the surface we are choosing is which is exposed surface, like this surface or this inner cavity surface. And field at the surface, let's say this surface has sigma charge density. Then let's say this small area element has sigma charge density. Then at any point, let's say I am zooming it. So this area will become like this flat. It has sigma charge density, and if I take a point very close to this sigma charge density surface, then the field at this point would be equal to sigma by 2 sigma by epsilon. How can I derive this? Simply by take a Gaussian surface like this, a cylindrical Gaussian surface or cuboidal. Let's say it has area dA. And in that case, the field is simply perpendicular to the surface. All over the surface, the field is E, and the area is dA. So the flux will be this, and by Gauss law we can say that the such a sigma into d is the charge divided by epsilon. So we can get this sigma, this electric field is equal to sigma by epsilon. This equation can be derived like this. So at the surface the sigma is equal to electric field is equal to sigma by epsilon. For a conductor at its surface, the field is this. This is because the field inside is zero. So the only flux is due to this part. So all the field is in same direction, which increases the value of the electric field twice. So it increases the value from sigma by 2 down to twice because all the field is in same direction, which contributes to the flux. And that's it. Now the next thing is potential due to whenever there is a surface, let's say this is a q charge surface, then its potential at its surface is equal to potential at its surface. Let's say this is a point at surface, then potential at A is equal to kq by r. We can say that V is inversely proportional to radius of this surface. So whenever there is a surface we have, then its potential is inversely proportional to r. We can also write it as the charge q can be written as, let's say this surface has sigma charge density, which is sigma charge density. Okay, leave it. Useless. It is useless. Sometimes this property is useful in case of surface. For example, if there is a surface like this is a conductor. If I put a charge q here, it will get spreaded everywhere. It will get spreaded everywhere on the outer surface, and there would be a thin layer of charge here with variable sigma density here, sigma 1 here, sigma 2 here, different sigma charge densities everywhere. And where the where the radius is small, let's say this is the surface and this is like an arc. This surface is like an arc, it has some radius of curvature r, and the lesser is the radius of curvature, the greater is the sigma. Means for a smaller radius of curvature values here, let's say this has very large curvature, so its sigma would be less, and it has very small curvature, so its sigma would be very high. So lesser the radius of curvature of the surface, higher is the sigma, if I am right. If I am right. So now next thing is capacitance. But before the capacitance, let's talk about electrostatic pressure. Electrostatic pressure is simply pressure due to electric force. Pressure due to, this is the pressure due to electric force on a charged surface. So let's say there is an electric field here E, and there is a small area dA of sigma charge density. Then the charge on this body is sigma into, so the dq is equal to sigma into dA, and the force on this body would be equal to, force factor is equal to electric field times sigma dA. That is the force acting on this body. So the equation of pressure is F perpendicular divided by the dA. The force acting perpendicular to this surface, the small force acting perpendicular to the surface on over this area divided by the perpendicular component of this force. Let's say there is an area here and there is a force all over on this surface acting F force, and this is the area vector, and the area value is dA. Then this is area vector, and this makes theta angle with this. So we have to take the component, perpendicular component of the force with surface, which means F parallel to dA over F perpendicular to surface. So this is perpendicular to surface. So the force acting perpendicular to the surface, which will be F cos theta, and now dividing it by dA here, we will get pressure acting on this area. So simply here we will get equation of pressure is simply E dot dA unit vector multiplied by sigma dA divided by dA, that is equal to sigma E vector dot dA unit vector. This becomes the equation of pressure acting at any small element. So the formula of pressure would become simply this sigma times electric field of dA. And if you want to find the pressure over a large surface area, so we will have to find the average pressure, which is equal to the F total perpendicular divided by the total area total of this surface. Now this was the concept of pressure, electrostatic pressure. Now we study only one type of case here important, that when there is a conductor, there is a metal or conductor that is closed, a closed conductor, then if it is given some charge, let's say q, then it gets spread all over the surface with different sigma charge densities all over the surface. Like this has less curvature, this will have high sigma, while this has very large radius of curvature, this will have very low sigma value. So this is how the charge spreads all over it. And the electric field at any the electric field at this surface, we know that the electric field just outside this surface of a conductor is given by sigma by epsilon. This is the formula of electric field at the surface, just outside the surface. If I take this surface, let's say this is a thin metal conductor and it has some sigma charge at this area. I am considering this dA area element here. It has some sigma charge density. Then the electric field just outside this surface would be sigma by epsilon, and the electric field just outside the surface is sigma by epsilon. And we know that the electric field due to this dA element is equal to sigma by 2 epsilon. The electric field due to this small element is small element will act like an infinitely large surface, and the field here would be equal to sigma by 2 epsilon due to this surface. And there would be some extra electric field due to the rest part of the system. The rest part of the system also applies some electric field here, E, which we call it as E rest. So E rest, we get E rest, which is in this direction, plus sigma by 2 epsilon, which is the electric field due to this. These two get added to give sigma by epsilon. So this E rest must be equal to sigma by 2 epsilon. This is right. The electric field due to the rest of the system at this place would be equal to the sigma by 2 epsilon, which is equal to the field due to this surface in this direction, which is sigma by 2 epsilon, and the E rest applying in this direction. These two get added and give a zero field inside and here in this region. So the electric field just at the surface, just below the surface, is this, just below the surface. This is the electric field just below surface. And the force acting on a body is not due to the electric field of this body. Means if I have a charge here, let's say q, and there is a charge here, let's say q1, this is q2, then the force on this q2, then the force on this charge q2 to the left will be due to the electric field of q1. The force on this charge will be due to the electric field due to the q1, not due to the electric field of q2. It will not feel the electric field of itself. A charge cannot feel the electric field of itself. So a system will feel, so a charge will not feel the electric field of itself. It will feel the electric field due to the other charges only. So we will, so when we calculate the electric field force on this charge Q2, we will find the electric field due to the Q1 and multiplied by the charge Q2. We will not use the electric field due to the Q2 in this case. Similarly, the force on this element will be due to the electric field of this S part, which is equal to sigma by 2 epsilon naught. Then multiplying this field by the charge, which is sigma dA, this will become the force which is perpendicular to the surface divided by the area. This get cancelled. The pressure becomes this. So the equation of pressure at this surface will become sigma square by 2 epsilon naught. So whenever there is a metallic conductor, it behaves like a balloon which tries to expand. It tries to expand. Each point on its surface is feeling a pressure which is given by sigma square by 2 epsilon. And if I use this electric field, this electric field is just outside surface, just outside surface. This is the electric field just outside surface. And then if I use this equation, which is just, let's say I will use the symbol for this electric field E outside EO, which is equal to sigma by A. Then in this case I will write pressure is equal to sigma can be replaced by epsilon E naught EO into epsilon square, EO into epsilon whole square, which is EO square epsilon square divided by 2 epsilon, which is equal to epsilon electric field just outside is square divided by 2. So it is equal to the pressure is equal to the electrostatic pressure on a metallic conductor surface is equal to the epsilon into electric field just outside the surface, is squared divided by 2. This is the formula made here for the electrostatic pressure, and we can also memorize this formula for pressure also. Simple to calculate. Now that is for the thin surface of metal. This formula was for thin surface of metal. In other cases, we will simply use this type of equation. We will simply take the sigma charge density and dA element and multiply by the electric field divided by the dA area. This will give the pressure for any location. Now moving ahead, we know that the pressure into volume, this value is equal to energy. This has unit of energy. This value has unit of energy. So pressure into volume must be energy. So if I say pressure, electrostatic pressure, then it means energy density, which is energy per unit volume. So pressure means energy per unit volume. This is one thing we should note also. Now moving ahead from pressure to energy, self energy. This was the electrostatic pressure due to the body itself, applying on itself. There is one more thing which is called self energy. This is for a system of charge. For a system of charge. For system of charge. Let's say there is a hollow sphere. First is this. There is a hollow sphere. There is a hollow sphere here, and it has some sigma charge density and charge q. Since it has charge q, then each small dq charge here on its body will have some potential energy due to the charge at other positions, let's say dq. at other locations. This will give some du potential energy. Each of them will give some potential energy du, and taking the sum of all this potential energy, we will get total potential energy of this whole system. So the whole system's potential energy will be equal to the summation of the individual potential energies. And if I calculate this whole energy, I will find out the value to be equal to, and I can find this by using integration of the small elemental potential energies also. And here the formula for potential energy: self potential energy for this hollow sphere. This is hollow sphere. For this hollow sphere, Ks is equal to k q square by 2r, which can be simply calculated in a the thought process. The thought process for calculating this thing is like, let's say this system, this sphere, this is a metallic sphere, metal, and there is zero charge right now on it. It has radius r and it has zero charge on it right now. Now there is some charge I am bringing on its surface from dq. Dq's charge I am placing on its surface from infinite positions. I am bringing it from infinite position to this surface. So initially it had zero charge, and the potential energy, and the work done to bring this dq charge from this point to this point would be equal to the electric field due to the system into dq integration with dx from infinity to this r radius. This is the potential energy du. Now taking the integration of all these du values, taking the integration of all these du values, we will get the potential, we will get the total potential is here. We know that when the charge on this body is q, and the potential is q, then the what we say, if there is q charge on this body, if there is q charge on this body, then the potential at its surface v is equal to kq by r. This is the potential at this surface when there is charge q. And if the charge is at infinite position, let's say dq charge is at infinite position, its potential energy is zero, and I am taking it from this position to this position. At this position, when I take this dq charge, the potential energy for this dq charge will be dq times v, which is equal to dq times kq by r. So now simply taking the integration of du with kq dq over r integration, if I take dq charge where I start from zero charge here, and I keep putting the charge from infinity to this point and till the charge becomes q here. So we will integrate from 0 to q, and this value will become 0 q square by 2r. This is the potential energy equation we used here, we found here. So simply the potential energy at this point on dq charge will be this. The final position energy, final potential energy at this point will be v into dq, and the initial potential energy of this dq was 0 into dq, which is potential at infinity is 0. This was simple integration. So this was for hollow sphere. Similarly, for solid sphere, let's say this is solid sphere. of any row density, it has total charge, let's say q, radius r. Then to make this system, thus there would be we would have needed some energy to create this system, and that system's energy is called set potential energy, which is equal to 3 by 5 k q square by r. In this case this was 1 by 2, in this case this is 3 by 5. This is solid, this is hollow, and this was simply the self energy concept. Now next topic is the next topic is electrostatic energy. Energy in electric field. When there is an electric field, let's say there is a medium here, it has electric field, and the medium has permeability value epsilon. Permittivity of the medium is epsilon. So the density of energy in the electric field, the energy of this electric field will have some energy in some volume, and the energy density, which I am denoting by this rho sign, rho of energy in electric field is equal to 1 by 2 electric field at this region epsilon times electric field square. So if the electric field in this region is epsilon E, and the medium has permittivity E, then the density of the energy in that region is epsilon E square by 2, and the energy in the dV volume is equal to, this rho energy times dV, which is equal to epsilon E square divided by 2 times the volume. So the energy in a volume is equal to the energy density multiplied by the volume. And if E is variable, then we have to take integration E square epsilon by 2 dV. We have to take the integration of this to calculate the total energy. Total energy in the volume V. For total energy in the volume V, we have to take the integration like this. If E is not constant, if E is constant, then simply we will write E square epsilon by 2 into V. Also E can also be variable, so this can also cause some integration need. Okay, so this was the energy stored formula. Whenever there is some energy, whenever there is some electric field in the system, there is some energy in this region. If there is some electric field, then there would be some energy in this region in the volume. Now next topic is let's say we want to verify this energy of field formula. Let's say there is a charge. There is a Let's say this is a metal of sigma charge here. There is a sigma charge here, sigma charge density here. Let's say the charge on this body is q. At this surface it is radius r, and the and what do we say now? Let's say this surface is negative charge of some another density and has negative q value, and So the electric field outside will be equal to 0. The electric field outside will be equal to 0, and the only electric field would be in this region, from this positive to negative charge. All the electric field is present between these regions. Let's say this is R1 radius and this is R2 radius. So now here the electric field in this region is given. The electric field due to this outer cell, this is hollow sphere. The electric field due to the outer cell inside this will be 0. So the electric field in this region would be only due to this Q charge. And since the point P is taken outside this cell, we can treat this at this center point. So the field due to this Q charge, Q cell charged at this point P would be equal to the distance from this point to this R, which is KQ over R square. This would be the formula of electric field. So if I take this formula, I will get I will get the density of energy. I will get the density of energy in this region at any r radius. Density of energy at any r radius is equal to kq by r whole square into epsilon naught divided by 2. This is the density. Now multiplying by the volume, we will get the energy. This is the energy, the small energy element in a small volume. Let's say this is a small cell. This is a small cell. Its volume would be equal to 4 pi, let's say r square into dr. So the volume multiplying by the volume will be this, and we will get the formula k square q square epsilon by 2 into 4 pi r square cancelled. We get 1 r square below, and this will become the integration of this total energy, which is integrated from R1 to R2. So this will give the energy, total energy equal to, when we integrate this we get the total energy equal to k square q square epsilon k square q square epsilon pi 4 by 2 is 2 simply, so it will be 2 k square q square epsilon pi, and the integration this will give 1 upon r1 minus 1 upon r2. So we are taking it from the r1 to the r2, so this will become r2 minus r1. We are integrating from R1 to the R2, where R2 is the larger radius, R1 is the smaller radius. This will give a negative sign. Okay. Anything? Okay. We forgot one more thing, that when we integrate, we will get a negative sign here. So negative. We will reverse the order again. R1 minus R2. So the integration of this will give the energy equation like this, and that's it. And let's say we will take another question for the calculation of this energy, and we will verify the self energy using this concept of energy density. Let's say there is a sphere, hollow sphere of some carrying some charge q uniformly at its radius r. So the electric field will be present in the system here. Electric field inside will be zero. So the electric field is only present here, and the electric field at any point outside is simply kq by r square, just like we did before. And simply here we will do the energy density is equal to E square. This is the value of E. This is E square epsilon by 2, which gives k square q square by r to the power 4 in divided by 2 and 2 epsilon. That's it. Now the small dE energy in a small thin cell area I have considered of dr thickness at any dr and any r radius, that would be equal to the density into volume. Density is k square q square epsilon by r to the power 4 into 2. Volume is 4 pi r square dr. This cancels this, we get r to the power 2. This cancels this, we get 2 here. And now simply we have to integrate it. We will get integration of both will give total energy in this space is stored is k square 2 pi q square epsilon bracket. We are taking it from this position to the infinite position. The value will become this radius 1 upon r minus 1 upon infinity, which will become 0. So the value will become simply 1 upon r, and this will become, I can write 2 pi epsilon naught s. If I multiply by 2 above and 2 below, multiply by 2 and below, above and below, this will become 4 pi epsilon naught divided by 2. So this equation becomes k. This will become 1 upon k. So k cancels k. We will get k upon 2 into q square upon r. And if you remember the self potential energy of a hollow sphere, it was the self potential energy. The self energy of the hollow sphere was k q square by 2r, which is this. So we have verified using this concept of energy density that this formula is correct for calculation of energy. Now the next concept is capacitor. Next concept is capacitor. What is a capacitor? Capacitor is generally any conductor. It is generally a conductor which can store charge. The word capacitor comes from the word capacity, which means storing something, which is related to storing something. It has some capacity to store something, contain something. So that storing of charge, that device is called capacitor. Capacitor is a device that can store charge. And whenever we have some charge, q in any system, there is always some potential associated to some points p around this system. So when we have a system of charge q there, then at any point p around this system, there would be some potential at this point p, vp, associated always. So what is a capacitor? A capacitor is a device whose capacitance is defined as charge stored per volt, where this voltage is the potential difference. This is the potential difference, and this is the charge stored in device. and device means, and this potential difference is taken along, this potential difference is taken over the device, or over the region, over the region over the region in which electric field exists. So if I say that there is a body here, let's say this is a hollow sphere, this is a metallic sphere, let's say metallic sphere, hollow sphere, and if I store some charge q here, this is radius r, then there would be electric field is 0 here. So the electric field in this system is from this point to the infinity. So the electric field exists between this point and the infinity. So the potential difference V will be taken from between this point and the infinity. So the potential difference at this point is kq by r. Potential difference at this point is 0. So the potential difference for this device will be potential at this point, potential V at starting point of, this is the potential at starting point of electric field, and this is the V infinity at end point of electric field. So we have to take the potential difference between the starting point of the electric field and the ending point of the electric field. This will be the potential we will put here, and q is the charge given to the device. This is our device. So we will assume that this device has charge q stored. So the capacitance of the device will be C is equal to q stored divided by the potential difference kq by r. Q cancels q, we will get r by k. This is the capacitance of this hollow sphere, conducting sphere hollow. Now moving ahead, let's say there is one conductor here, there is one conductor here, okay, and both are neutral, both are having zero charge right now, both are having q is equal to 0, q is equal to 0, both are having q equal to 0. Now if I put some q charge in this plate, let's say I put some q charge in this plate, and then in that case there will be some negative charge from inside here and some positive charge from outside here. The total charge on this body, on this surface, the sum of this negative and positive charge is equal to 0, and the charge produced outside is equal to q, and the charge produced inside is equal to minus q. We will talk about why this happens later, but first assume that there is some minus q charge in this inner surface of this cell. This is a cell of some thickness. The inner side has some minus q charge spread over, and the outer side has some plus q charge spread over. And in this case, let's say I am grounding this outer surface. So the potential, since the potential of earth is equal to 0, the potential of this point should be equal to 0. So to make the potential at this point equal to 0, the potential due to these 2 points is 0 at this location. So this positive charge should become 0. Means when I ground this outer surface, this was the inner surface given q charge, this is the outer surface, this is the outer cell. The inner charge got some negative charge, the outer side has some positive charge, but when I grounded it, it lost its charge and there was only negative charge inside of minus q charge, and here in this surface the charge was 0. So now in such kind of system where this outer surface is grounded, this is a conductor, this is also a conductor, all charge is at the surface. Let's say this is r1 radius and this is r2 radius. Then in this case the electric field will go outward like this, from positive to negative. The electric field starts from this point and ends at this point. Conductor cannot have electric field. Electric field is equal to 0 in this region, electric field is equal to 0 in this region, and electric field is equal to 0 in this region, because this is minus q charge over in this region and q charge in this region. So q and minus q charge total will give kq by r square minus kq by r square. The sum of these two will give net electric field at any point p outside is equal to 0. So field is 0 here, field is 0 here, field is 0 inside. Field is only present between these two regions, these two sides. So the capacitor in this case form is having electric field starting at this point, ending at this point. So capacitance will be given by the charge q stored here and the potential difference of this point at this point A and this point B. So V will be equal to VA minus VB. We will always take the magnitude of the potential. We will take the magnitude of the potential. So that is equal to VA is equal to KQ by R1, and the potential due to this negative charges, so KQ by R2 minus KQ by, the negative charge will have constant potential inside due to it, so we will say KQ by R2 due to the outer surface, and due to the inner surface, let's first find the VA. The VA value is equal to, due to the inner surface, inner charge surface, the potential at point A will be equal to KQ by R1, and the potential at B point is equal to the potential due to this A at this region and due to this at this region, that will be equal to KQ by R2 minus KQ by R2. Both will have the same, both are having the same equation of potential. So the potential at B point is 0. So the potential difference VA minus VB is equal to this, which will be equal to KQ bracket 1 upon R1 minus 1 upon R2. So the potential difference is equal to this KQ upon R1 minus R2, 1 upon R1 minus R2. So the potential will be equal to KQ R1 minus 1 upon R2. So the capacitance of this device will become C is equal to, we will take R1 minus R2 here, R1 into R2 here. So the capacitance of this device will become this. So according to the basic concepts of this capacitor, we can derive the equation of this capacitance of any type of device. When we have a capacitor, we generally have some charge q at one surface, and we always have, when we talk about capacitance, we always have two bodies. In this case, first body was this and second body was there, and these two bodies have equal and opposite charge. This had positive q charge and this had negative q charge. But when I took the case of single hollow surface which is charged by q, it had only one body of charge q. But we can assume that at infinite location, from this surface, there is a very large surface of, let's say, radius r, which is tending to which is tending to infinity. This radius of this large surface is tending to infinity and it has charge q. So we can assume that there is another body, but it is at infinite location. We cannot see it. So even though we had only one body here, we can assume that there is another body of charge minus q at infinite location. And in case of, let's say there is a parallel capacitor. Let's say we have a parallel capacitor here. Let's say we have only a plate here. I give it some charge q. When I give it some charge q, let's say it is a very large plate, then the electric field in this region is simply sigma by 2 epsilon. That is the electric field, and this electric field starts from this point and goes to the infinity. Since the electric field is constant everywhere, dV will be equal to 0. No, dV will not be equal to 0. E is equal to constant, E dot dx will be equal to minus dV. So potential at infinite location is equal to 0 according to our assumptions. So if I take a point from this location and take a distance r from this, then the potential at r distance from this plate would be equal to, let's say this is charge q of sigma charge density. This plate has area A. Then if I integrate this value is constant. The integration of this simply will give integration of dx from infinity to r. This is not a defined quantity probably. Maybe, ouch, this will look like this. This will become sigma by 2 epsilon naught epsilon r minus infinity. The equation will become like this. If I can take this part of this equation, let's say the reference point I am taken is at, let's say, r naught distance from this point. This is the reference point. So I am taking this reference point, this potential at this reference point is 0. V at this reference point is equal to 0. Then in such cases, I can say that the value of potential at r distance is sigma by 2 epsilon naught r. If I assume that this potential at this location is 0, then I can say, if I take a fixed value of this location, if I take this potential at this location to be 0, so I have to take a constant value. In case of writing this, Vr will be equal to some quantity we are getting here is sigma by 2 epsilon, something like this, into r minus some constant value V naught. And this is a very large value, but it is a constant value. We can avoid this value also, and the value of this potential becomes this. In case of parallel plate capacitor, we will see that if there is a parallel plate capacitor and I join this capacitor, this is of area A, and if I take some q charge from this side and put it to this side, this will get some negative q charge and this will give some positive q charge. And this area is A. If this is a very large plate, then the sigma will become q by A. And in this case, the electric field will start emanating from this point to this point. Electric field at this region would be equal to 0. Electric field at this region would be equal to 0. Electric field will only be present in this region. So the potential, let's say this is point A, this is point B. So potential at A minus potential at B, that is simply equal to the integration of V final minus V initial from this point to this point we have to go, and since we are going from this point to this point and the direction is negative, this will become positive, and this length integration will give the length. Let's say this length is d, so the value of this potential difference become ed. Now the capacitance will be equal to the charge stored q divided by ed, and the value of electric field is equal to, in this region the electric field value is equal to sigma by epsilon. How? The electric field due to this negative surface charge density is sigma by 2 epsilon in this direction, and due to this place is also in this direction of same value, sum of both electric fields will give sigma by epsilon. So replacing E with sigma by epsilon, we get q upon sigma d epsilon, and this sigma q charge can be written as sigma into a. This becomes a epsilon by d. So the formula of capacitance for this parallel plate will become this epsilon into E by d, which can be written as a into epsilon naught k by d, where d is the gap between them. This is a very important part. Now we have done some capacitance steps. Now another point about capacitor is that when there is a capacitive plate here, let's say I have a q charge here and there is a conductor here. This is, let's say, conductor here, and this surface is q charge. This surface is q charge uniformly distributed. Then in such cases this conductor will produce some negative charge in this side and some positive charge on this side. It will become polarized. This is a conductor and this surface is some positive charge q, and the magnitude of the charge inside this region, since this is a conductor, the charge inside will be equal to 0. All the charge will lie on the surface of this conductor, means at this surface and at this surface all the charge will lie, and the surface and the charge here will be equal to minus q, and all the charges over here will be equal to plus q. So that the sum of these two charges is equal to 0, because the conductor was initially neutral. It was initially neutral, so the sum of these two charges will be equal to 0. That is the conservation of charge. And when q charge faces a conductor, there is equal and opposite charge. Developed in this side. So if there is a minus q charge surface here, and if there is a conductor here, this is conductor. If I place it here, then this conductor will produce some positive charge here of magnitude q in this region, equal and opposite to this charge. And there are some important points about these cases, that in case of conductor, when the conductor is isolated, there is no electric field, then the whole charge is uniformly distributed, and if it is not in not in zero electric field, then the charge is distributed but not uniformly. In case of non-conductor, the charge is not distributed, and when there are group of calculates, then electric field inside each conductor will be 0, and the way to calculate the charge stored at any side is like this. Let's say there are some plates P1, P2, P3 dot 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 here. Let's say there is plate P1, plate P2, and dot dot dot. There are many plates in series like this, placed one by one, and the charge stored the charge is stored in this side. The charge is stored in this side if these all plates are very close. If these all plates are very close, and then in this case, if this side has charge q1, then the let's say this is the last plate pn, then this side has charge also equal to this q1 value. If this side has charge q1, then this side will have charge q1 also, but p1 and pn, these two have equal charge, and that is equal to the charge on all the plates. And the sum of what is this saying is, one second. So let's say there are some pn plates here, and they initially at the starting they have some charges, let's say q1, q2, q3, q4 on their body. They have net charge q1, q2, q3, qn on their body, qn. Then the total charge on this system, the total charge on the sum of the total charge on all plates would be q1 plus q2 plus q3 qn. And what we have to do is, let's say the total charge, that is q total, we will call it q total, the sum of the charge on all the plates, that is equal to q total. This is the initial state. This is some charge stored in its body. Now when they are placed closer, now they are bring closer to each other, and after they are bring closer to each other, this side, this is the first plate and this is the last plate. Then in this case, this plate, on this side of this plate, there will be some charge, let's say q naught, and on this side of this plate there will also be a charge q naught. Both these end plates, the extreme plates, on their outer sides will have q naught charge, and the q naught charge is equal to q total divided by 2. Means the total charge stored at this side and at this side, this is equal to the half of the total charge on all the body. Half of the total charge on the whole body. This is q total divided by 2. So the charge stored in these two bodies on this sides is equal to this. And the second property, this is the first thing. This is the first thing we have. The second thing is total charge on a body. Total charge on a plate is conserved. So when the charge redistribution happens in a plate, then the total charge on the body will still be q1. Means if there is a charge, let's say 3 coulomb in this body, and if the charge redistributes, let's say this side gets 5 coulomb positive charge, then this side will give minus 2 coulomb negative, minus 2 coulomb charge, so that the sum of these two values will give 3 coulomb charge. So the total charge on the plate will be constant, conserved. This is the second point. And third important point is that the facing plates have facing sides of plate have equal charge. Means if this side has, let's say q dash charge, then this side will have, sorry, equal and opposite charge, minus q dash charge. Facing sides of plate have opposite and equal charged. Opposite and equal charge. Equal and opposite charge. So if, let's say there are two plates here, if this side has, these are two conductors, and if this side has, let's say, 5 coulomb, then this side will have minus 5 coulomb. These two will have equal and opposite charge. So if this has q dash charge, then this will have q dash charge minus q dash charge. So in this way we can write the total charge distribution all over the plates using these three things. Okay, now moving ahead, we will take one example. Let's say editing example of video. We have one plate here and one another plate here. This plate had 6 coulomb charge. This plate had 8 coulomb charge. Now these are conductors. These two conductors are plate. Now they are bring closer. 8 coulomb charge here. When they are bring closer, what happens is that first we have to find the charge at these outer plates. Which is equal to q naught, and q naught is equal to 6 plus 8 by 2, which is equal to 14 by 2, which is equal to 7 coulomb. 7 coulomb. Here it was 8 coulomb. So the charge at this side would be equal to 7 coulomb, and also at this side it would be equal to 7 coulomb. Since this is 6 coulomb and this is 7 coulomb, to conserve the charge on this body, this side must have minus 1 coulomb. Similarly, this side will have, to conserve this, will have 1 coulomb. And if you see that the opposite sides have equal and opposite charge, minus 1 coulomb plus 1 coulomb. That's it. Now take a system of 3 plates. When there are 3 plates, let's say it has 3 coulomb, it has 5 coulomb, coulomb, and this has, let's say, 6 coulomb, or let's say 4 coulomb. Now in this case, when these plates are placed closer, then what happens is that this side and this side, first we will find the charge at these sides. This would be equal to q naught is equal to sum of all these, which is 5 3 8 plus 4, which is 12. 8 plus 4 is 12 divided by 2, which is 6 coulomb. So this side will have 6 coulomb, this side will have 6 coulomb. And now we will get conservation here. We cannot tell the charge at this side, at this plate instantly, but we can tell later. This side will have minus 3 coulomb, because the net total charge on this body is 3 coulomb. So minus 3 coulomb plus 6 coulomb is 3 coulomb. Similarly here we will get minus 2 coulomb. Now this is having minus 3 coulomb, so this will have plus 3 coulomb, and this will have plus 2 coulomb. The sum of these two is equal to 5 coulomb, which is correct. So this is the solution of this problem, distribution of charge. That's it. The chapter of capacitance. Okay. Now there are some more facts about capacitance. We have to more things in the capacitance chapters we have to deal. Let's say there is a, we will talk about parallel plate capacitor now. There is a capacitor, let's say here, there is a capacitor here. This plate is charged sigma and this is charged minus sigma. This is area A and this is area A also. They have distance d between them, and the dielectric constant between them is k. Then what happens is that this sigma charge will produce an electric field in this region. E is equal to sigma y to epsilon. This charge plate will produce electric field is equal to sigma y to epsilon. Here we will use epsilon naught, not epsilon. because epsilon is taken when we want epsilon is used when we want to find the electric field due to the system and the medium, means the effect of medium. When we want to consider the effect of medium, we will use epsilon, but in this case I am not considering the effect of medium right now, so I am only taking the field due to this charge. So this that's why I will use epsilon naught here. Similarly, this charge will also produce field here like this. This will have field in this direction sigma by 2 epsilon naught. Be careful with this. Epsilon is used when we want to include the effect of medium, but here I am not including the effect of medium. Due to this, I am just only finding the field due to these charges, not due to this medium. I am not including this right now. I will include this later. So then electric field, I will call the electric field applied. Electric field applied is equal to, let's say, E naught. E naught provided is equal to the sum of these two fields, which is this is providing field in this direction, this is also providing field in this direction. So the sum is sigma by epsilon naught. This is the applied field. Now what happens is that there is a dielectric medium here used. What happens is that when there is an electric field here in this, let's say there is an electric field here, the atoms in this medium, they have charge like positive charge and electron rotating. When we provide an electric field in this case, the electrons are pulled in the opposite direction and positive charge is forced in this direction. So what happens is that the positive charge will remain at its place, but the electron will get shifted toward this side. So this will become negative little bit, this will get polarized, this side will become little bit negative, and this side will become little bit positive. We will write it as positive delta positive charge, and this is delta negative charge produced in this case. And this delta positive charge is found at the surface, and delta negative charge, since the electric field is pointing in this direction, the delta negative charge is found in this side. And since there is a series of atoms, atom by atom, there would be some delta negative here, delta positive here, delta negative here, delta positive here, and this goes on. But at the extreme ends, let's say this is parallel plate, then at the extreme end this side will have positive charge, and these two values will get cancelled out. This will become zero charge. This sigma negative and sigma delta positive and delta negative will also give zero until we reach this end of plate where this is delta negative charge and it not get cancelled. All the internal, all the fields, all the charges inside will get cancelled and nullified, but the charge at the end sides, it will not get nullified, and we have to consider that charge. Let's say due to this charge there will be some sigma p density in this region. This is positive, so this will be negative, and this is positive. This is dielectric medium, not a conductor, so there will be some sigma minus sigma p induced in this side due to the delta negative charge delta induced in this region, and due to delta positive region produced, there would be some sigma p charge density in this area. Now what happens is that these two will also produce some field, just like these two produced fields. The field due to these two is equal to, is in opposite direction of the supplied fields. So E due to the medium or dielectric, E due to the dielectric is equal to, let's say we will call it ED, which is equal to sigma, let's say this direction is, let's say this direction is n cap, and then this electric field is in this direction. This is sigma p by epsilon naught in minus n cap. Now the net electric field in this medium E net is equal to E plus ED in this medium, which is equal to sigma minus sigma p upon epsilon naught n cap, where n cap is in the direction of applied electric field. So this becomes the equation of E net. This is the equation of E net in this medium. Now the potential difference across these two plates will be equal to V is equal to E net time the gap between them is ED. So the potential difference between these 2 points is equal to V is equal to E net into D. We get which is the integration of electric field dV is equal to E net between into dx integration of this. So we get E net into D, which is E net is constant, which is equal to sigma minus sigma p divided by epsilon naught into D. This becomes the equation of electric field, sorry, potential. So we know that the capacitance of the charge is capacitance of a capacitor is simply Q by V, which is equal to sigma into A divided by potentially sigma minus sigma P into D epsilon naught. Now we know that this value is equal to epsilon naught by D A into epsilon naught by D into sigma minus sigma P. The dielectric constant value is equal to sigma upon sigma minus sigma P. That is the result here. This ratio sigma upon sigma minus sigma P, this is called the dielectric constant. This is the factor by which the electric field is